Hello, everyone. Thank you very much for coming to Brown Bag Seminar today. So today's speaker is Dr. Cathleen Jones. So she's a later scientist at NASA Jet Propulsion Laboratory, where her main research is focused on using radar remote sensing for studying natural disasters and monitoring critical infrastructure. Currently, she is the PI on NASA and DHS-funded pilot projects to develop methods to detect and quantify levee deformation, seepage, and general subsidence rates using remote sensing, with focus on Sacramento and San Joaquin Delta, and also recently California Aqueduct. So she received a Bachelor of Science in Physics from Texas A&M and a PhD in Physics from the California Institute of Technology. So with that, I'll give the talk to you. So please welcome Michelle with me.
So, thank you very much. Can you hear me? Good. So today I want to talk about a project that I've had for about 6 years now, trying to develop methods that use radar to detect threats to the levees. And the prototype area, the area that I've used for this prototype study was the Sacramento-San Joaquin Delta, which is very close to where I'm based in Pasadena, California, and very close to where the aircraft that I use with the radar is based also. So this has been a very convenient way for NASA to study levees on a big scale with this kind of pilot project. So, of course, as you probably well know, the Sacramento-San Joaquin Delta is a very critical water resource for the state. It's the most critical water resource in all of California, but it's also a vital ecosystem. And balancing that the weight between ecosystems and water resources is very delicate. The area has over 60 islands, and they are contained by about 1,100 miles of levees. Now, that is an incredible amount of levees. This is the second largest levee system in the United States, exceeded only by the Mississippi River levee system. So people across the country don't realize just how large the levee system is here and how critical it is. The area is a center for a lot of agriculture, for a lot of oil and gas production, for tourism, and a lot of people live there. And it collects runoff from 2/3 of the state and delivers it to residents across all of Southern California. However, because of the way this delta has been managed, it has subsided substantially, and most of the islands lie below mean sea level. So along the Mississippi River, you have a case where the levees are really only stressed during high water conditions, so flood conditions. But in the Sacramento Delta, 24 hours a day, 7 days a week, year in, year out, the levees are stressed. And so the maintenance of the levees in this area is extremely critical. The Sacramento Delta was formed back in before the 1880s when when levees were built so that the islands could be used for agriculture. Prior to the levees being built, you had a natural estuary, freshwater tidal marsh, where you had water-covered land, and the vegetation would die, form into soil, and you would get a natural balance between accretion and subsidence from anaerobic decay of the material. Once the islands were drained, however, you had a whole lot of new subsidence mechanisms. You had oxidation of the soil, which was a main cause of subsidence. You have compaction from dewatering of the soil. For a long time, you had wind-blown loss of soil from the area. That's not such a problem anymore because of the practices that have gone on. But this has been going on for, over 100 years, and now all of these islands are, most of these islands are below mean sea level. If you look at the map on the left-hand side, you can see that the dark blue islands, and there's only a few of them around the very edge, those are the only islands that are above mean sea level. And the most critical islands, of course, are the ones in the western delta, because if the levees fail there, then you get saltwater intrusion coming in at big scale from the San Francisco Bay. Just to make everything a little bit worse, you have major faults very close to the delta. The delta is here. You have the monster, the San Andreas Fault, 50 miles away. You have the monster's little sister over here, the Hayward, 30 miles away, and then you have a bunch of faults that are within 10 to 20 miles of the delta. And the shaking that could come from an earthquake on those faults could cause liquefaction or loss of multiple levees in the delta. So why do we consider using radar remote sensing for monitoring the levees? Well, in an area that's relatively large like this, with a large number of levees, you really can't use a ground-based visual surveys on the time scale with the frequency and the coverage that you need in order to have a consistent, continuous picture of what's going on. Remote sensing surveys can give you very large swath images of the area and very rapidly, and so you can make a rapid assessment of a snapshot of the conditions all across the delta at one time. Probably equally importantly, though, is that you can get consistent monitoring. You use the same technique to monitor every levee in the area, so you have relatively understanding of what's going on each island, which is very important to have consistent monitoring in an area like this. And of course, all the other things, if you're flying an airplane, you don't have to worry about getting into areas that are difficult to access. And but probably the most important thing, and I'm going to talk in more detail about this, is that if you use radar remote sensing, then you can detect changes that occur on very small scales and by very small amounts. So you can see something that nobody would detect with their eye, walking past, driving past or walking past or surveying in that way. So the goal of what we're doing is to develop techniques that could then be used to kind of inform a targeted monitoring program. We don't envision, getting rid of the ground surveying, but instead targeting the ground surveying so that you go to the areas that look like they have problems. And then, of course, doing this kind of a targeted monitoring program, of course, it's much more difficult than doing emergency response, so it would be available during emergency response. The project that I've had, it uses an airborne radar that's one of NASA's assets. It's shown here in flight over Palmdale, California. This project has been going on since 2009, so 6 years. The funding agency initially was NASA Applied Science. Since then, it's been funded by the Department of Homeland Security and now by the Department of Water Resources in California. We fly this aircraft over the Delta approximately every 7 weeks. There's been about 51 flights since 2009, July of 2009. And we image the area that's covered over here in this yellow box. So that area corresponds to 9 flight tracks. So we go east-west across the Delta, then we go north-south across the Delta. And what that means is that every area, every levee is covered by 3 lines. And so we get a view from different directions, and we get validation data, cross-validation data. So if you get a measurement in one line, you expect to get the same measurement in the other line. So So I'm going to be showing you a lot of images from radar, and I just want to start by showing you a radar image so that you get the picture of what radar image looks like. It's not a photograph or an optical image, and the most obvious thing is that the resolution is not what a photograph would be. So the resolution of this image is about 20 feet on a pixel. So you're not actually seeing the real colors on the ground, but there are great advantages of using radar. One of which is that radar is an active instrument. You're sending out a pulse towards the ground, and that pulse actually can go through clouds. So it can see through clouds. It images the surface day and night. It can, if there were a fire, it could see below the smoke and haze. So you can rapidly see the ground regardless of the day-night light conditions. It's also very good at detecting standing water. These areas are radar dark, we call them, because they have very low backscatter. And so you can very quickly pick out the areas that have standing water. And that's quite useful in a flood, for example. You can use different types of radar, and I'm going to give you an example, to identify the surface types. So you can tell, of course, water from land and from other structures on the land. And you can detect these very small changes in movement of the ground. And by very small, I mean a very small fraction of an inch. Millimeter scale changes can be detected at the ground. This is a very photogenic radar platform. This is NASA's UAV SAR. UAV does stand for Uninhabited Aerial Vehicle, and you can see that those windows indicate that this is not a UAV. It's actually deployed currently on a Gulfstream III aircraft. And the radar is here in a pod that hangs below the wings of the aircraft. This aircraft has been in operation as a science instrument for NASA since 2009. I just want to show you a little bit of the guts of the instrument because I actually helped to design the radar and have been involved in it from the very, very start. This is the pod. There are inlets at the front of the pod that provide ambient air cooling, so it's independent of the platform that it's mounted on. The antenna is here. It can be popped off, and a different antenna can be put on, and here are some examples of different antennas that we're able to put on. It operates at the same frequency as NASA's next Earth observing mission, so it's a prototype for NASA's upcoming NISAR mission. So we can use it to study, kind of to get a kickstart for studies that could be done with this satellite once it comes online. NASA has an open data policy, so any NASA data is available for free. It can be downloaded off the web, and that's another great advantage whenever you start looking at the cost of radar images from a commercial provider. At JPL, we have 2 complete copies of this whole pod, so that we can test with one and fly with the other if there's any problems. This is used for all kinds of experiments. It flies 500 science hours a year. It's been flying 400 to 500 science hours a year for 6-7 years now. Many studies are ongoing, in particular things like looking at volcanoes and earthquakes and fault slips and those kinds of things. But one of the studies has been the Levees study. The aircraft operates at 1.3 gigahertz, which means that it has a 10-inch wavelength for the radiation. And the way you think about that is the radiation, the wavelength tells you about the size of the structure that it's going to scatter from. So if you have a bunch of leaves on the top of a bush, it's going to penetrate through that bush and actually scatter from the ground. So this is a radar that can actually see below vegetation. Very useful whenever you want to study bare earth in an area like the Delta. It has very good resolution. Its resolution is less than 6 feet for a single pixel. It operates from 41,000 feet, and the swath width is 14 miles. So it flies over an area, images 14-mile wide swath by 200-mile long, however long it flies, and you get that area in about 20 minutes. And that's why we can fly up to Sacramento, fly 9 lines. We have about 2 hours of exactly what's happening. Well, what's happened, all of the images come from, are collected in about a 2-hour time period, 2 to 3 hour time period. But I want to talk, it's what's called a full polarization instrument. Now, the polarization of this instrument is exactly analogous to polarization of light, which you already understand. And so surfaces reflect differently from different polarizations. So, for example, you know, you put on your Polaroid sunglasses and it cuts out the backscatter from water. Well, that's exactly analogous to what's happening with this radar. You get different backscatter from different polarizations depending on what's on the surface.
Please
so
mute your phone.
This is an example. We call the polarizations horizontal and vertical polarization, just like you would think of for optical frequencies. And in our notation, VV means you scattered, you sent out a pulse vertical, and you measure the component that comes back in that same orientation. And likewise, HH is this way. And HV would be something where you send out one, and you receive in another. So something like a branch that's at an angle would cause that kind of thing to happen. You'll get more backscatter that changes the polarization when you have a structure that's at an angle. So what you see here is that water is brighter in the VV channel. Soil looks like a combination of the two channels. And whenever you add more water to the soil, it begins to look more and more like, you know, higher and higher VV. So you can tell something about this water content in the soil. And then this green is a false color for the cross-polarization channel, and it kind of picks up the vegetation. Probably the most important aspect of this type of radar imaging, though, is its use for doing this deformation, small-scale changes of the surface. And in order for that to happen, this aircraft flies a repeat track, and it can fly a repeat track to plus or minus 16 feet. So if I'm on this aircraft day one, I come back, I'm sitting in the same seat, same location within about 16 feet. And we're flying at 41,000 feet, and most aircraft fly barometric altitudes, so they can vary by 1,000 feet or more. This flies GPS altitude, so it's exactly the same distance from the ground. So once you fly that same distance from the ground, if you track the distance to the ground very carefully, and the ground moves, like it deforms in some way, you can measure that deformation accurately by doing a difference between the two images that you collect at the two different times. So this aircraft I show you, this is this tube right here, this outline here would be the 16 feet, and usually it's within about 3 feet, so plus or minus 1.5 feet is the accuracy of the repeat track. That's pretty impressive. So this is how this technique for measuring surface deformation works. It's called radar interferometry or synthetic aperture radar interferometry, or INSAR. The first time the plane flies over, it sends out a pulse. That pulse goes down to the ground. It scatters, and whenever it comes back, we measure, where it is in this single phase of the one wavelength. So we measure the time to the ground and back, and then we measure exactly where it is along that fraction of a wavelength. The next time, if you watch the surface, the next time we come through, the surface is moved, then that path length changes. And exactly where it is within, the wavelength changes. And so you can measure small fractions of the wavelength very well. This picture down here is kind of a color contour map of change around the Lost Hills oil field from oil extraction. And you see that one color wrap is about 5 inches, and so this is about 10 inches of change, 7 to 10 inches of change over this time period. So what do I want you to take away from this? This is used to measure surface deformation. If the surface is all jumbled up here, you cannot necessarily tell how much the surface moved, but you can tell that it changed a whole lot. And secondly, you only measure, of course, you're measuring along the way that the pulse went to the ground. That's called the line of sight direction. So you're really measuring not this full change in subsidence, but the fraction that's along your line of sight direction. So how can this be used for monitoring levees? If you look in the state's levee threat monitoring guidelines, they have a bunch of threats, and cracks in levees are one, seepage is another, slope instabilities. You can have a slump, you can have a slide or something along the slope. You can have sand boils and sinkholes, and of course you can also, what's not in here, you can have general subsidence across an area that causes the levees to drop down. And many of those can be detected if you can detect ground movement. So we started this project in July of 2009, and I'm going to show you some examples from the Western Delta. Sherman Island, Bradford Island, Webb, all these islands in the Western Delta, of examples of places that we found movement of either the land around the levees or of the levees themselves. 1 month after we started this project, there was a ship that actually rammed the north levee on Bradford Island. And this was kind of one of my favorite examples because it's extremely memorable to me. The aircraft was flying back from Alaska on a science deployment, and my collaborator at the Department of Water Resources called and said, "Can you image and see if you see anything that happened on this Bradford Island levee? And I'm not going to tell you where it was. You're going to have to look at this and tell me where the levee, where this happened." So of course this was like throwing down the gauntlet. What am I going to do? So we actually diverted the plane. It refueled. It collected all these images over the Delta. And whenever I looked at the data, I could actually pick out this green line is the healthy levee, and this is the point where the levee was impacted. So this is an example where the impact was so great that I couldn't actually measure the amount of deformation, but I could tell that something had moved a whole lot along this stretch of levee. And this is a photograph of that area that had been affected. So after that, of course, the state's interested in how this new levee is holding up, what's happening with this new levee. And so one thing that we've been doing post-repair is looking at the rate of subsidence of that stretch of levee. So I have two examples here. This point along the stretch of levee that was repaired, and an inland point. And inland, this is a plot of the displacement that occurred as a function of time. So each of these points on the graph is a measurement from one of our flights. So what you see is that inland you get kind of some seasonal trend with a small amount of seasonal trend with a very small amount of subsidence on it. On the repaired levee section, what we see is sort of an exponential decay following the repair. You've added material, you weigh down the levee, you get some compaction, and so and then it settles out over time. So this is 2009, and this is 2014. So it behaved exactly like one would have predicted it would, based on what you would expect of adding soil to a particular area. In Sherman Island, I'm going to show you a bunch of examples from Sherman Island. The first example is kind of on an area of the levee that's on the southwest side. There's just kind of a hint that there's something different in this stretch of levee from our signal. The blue colors are more subsidence and the yellows are less. But if you go out and you drive along that stretch of levee, you actually find a dip in the road right there. So this is an area where we've confirmed that we are actually detecting a problem with the levee. On Sherman Island, if you can see, one thing we see is that there's a great variability between the amount of subsidence that occurs inland in different fields. This is an example from the western side of Sherman, called the Whale's Mouth, where inland at this point, you see, really large seasonal trend and very, negligible subsidence at that location. Just a short distance away, maybe a mile away, at this point, however, you see that same seasonal variation on top of a much larger subsidence rate. I show this example first because I want to emphasize that if I came through and I measured, very, very infrequently, I would not be able to tell what was seasonal change from what was this long-term trend. The seasonal change is substantial in this area, and the seasonal variation is larger in many areas than the subsidence. So you need to measure as frequently as I've been measuring in order to detect this subsidence rates and be able to tell where the problem spots are. This is an area up here. The photograph of the area shows nothing particularly going on, but the radar sees a very distinct subsidence trend across that region. And this is an area where repairs were done relatively recently. Probably this is new fill subsiding. So you pack material on and it begins to subside. But this is something that, you would not drive along this road and know that there was that big of a change. And the radar is actually, quite good at detecting this kind of change. So you've probably noticed this extremely blue area down here. If we focus in on it, this is a Scalar Pond. So in the past, there was a levee break at this location. It scooped out a bunch of sand, and now after post-levee repair, you have a lake there, kind of a pond there in that area. And all along the levee, which is right here, kind of in yellow, and inland from the levee, you see very large subsidence. The levee in these locations are fairly stable, so this is a new stretch of levee and it's pretty stable. But inland, you're getting, 25 centimeters of subsidence, so 10 inches of subsidence over a 5-year period. Now, your eyeball is not going to tell you 2 inches over 1 year. But for the radar, this is like the worst area in the delta that we've seen. It's huge. It's huge for the radar. This is a site that we've instrumented recently, and we're going to use it as a validation site so that I can remove all of this preliminary. We have ground measurements, and we have radar measurements, and we validate the two against it. I think that's really critical, and it's something that's kind of expensive to do, and so we've been building up to get enough funding to instrument this site. I think we plan to finish that collection of validation by the end of this year. I want to show a few things that are going on Jersey Island, a couple of areas that I picked out right across from Sherman. Sherman's up there. In this area, the colors aren't quite as good as I'd like, but along this area, you see subsidence kind of centered in the fields off of the levee, and it does seem to be affecting the levee. But the waterside slope, which is this green line here, is fairly stable in that area. On the other hand, you go, slightly east from there, and you see a similar thing going on in a field, but you see a stretch where the waterside slope is being affected. And we can actually differentiate, something that's happening on the waterside slope from something that's happening on the landside slope with this particular radar. And then if you look at the Line Point Peninsula on Jersey, you see an area where the levee was probably recently repaired, or sometime in the past 10 years repaired, and you see subsidence from that. You see subsidence inland in this area, just in general, and then on this part, the levee is actually very stable. So another example, I'm going to just show you a bunch of examples. This is WebTrack. Subsidence across the whole island is generally low. In this one area, you see subsidence of the levee, and you see subsidence inland from the levee. This is not an area that's been recently repaired, so it's an area that one would, flag as needing watching based on this kind of data. And then on Holland Track, this whole stretch of levee from, I believe, here to here was repaired, but only some stretches are subsiding post-repair. And probably that indicates that there's some difference in the soil underneath, very relatively localized changes in the soil type, and so you get different responses of the soil to the loading from the fill. And that loading from the fill seems to be extending inland from the levee, so it has an effect past where the load was placed. So that's what it appears to be happening in these particular locations. Mandeville Island, this is in the center of the delta. This is the island that has experienced the most subsidence in the delta. This is an area, in general, the levees look pretty good. This is an area where you see the same thing as I was pointing out on Jersey, where, inland you see, some modest subsidence trend, but at this one stretch of levee you see a much larger trend of subsidence. So that's kind of my grab bag of examples of what you could do with this technology. I think it's really game-changing in a way. It really can tell you in a very rapid way what's going on across a large area. But I want to just spend a few minutes talking about another indicator, which is not something that you use this interferometric technique to get at, and that's seepage. It was kind of serendipitous for us, actually. We went out and we flew 3 imagings of the delta in one day, and we chose the day in the summer when you have the highest tidal extremes. And so we flew at low tide, we flew at mid tide, and we flew at high tide. And the idea was to look for changes in the elevation based upon the tidal level. And we didn't particularly see much change from that, but what we did see was a huge decorrelation in this one area. And okay, look, I think high tide was 3 a.m., our mid tide was 6 a.m. We just didn't believe that farmers were out there doing a whole lot between 3 and 6 a.m. So that doesn't leave a lot of things that it could be. It could be, you know, sheep grazing or something like that, or it could be seepage because the water, you know, is changing in the channel next to it. So we identified this stretch of levee, and we went out and actually, you know, found a seep at that location. The next year, we repeated the same test, and we found an area that had a seep and was repaired, and we confirmed that that was a seep that had been repaired over that time interval. So this is kind of cool. It was kind of totally serendipitous that you could use this data to identify seeps. And I think that seeps are important, but deformation of the levees is probably more important. These levees, they seep a lot. They probably seep a lot. It's good to know that because you want to know because, you know, for example, maybe during an earthquake, those would be areas that are more subject to liquefaction because they have more higher water content. So it's very good to know. But it's not, I think the focus of our study has been to look for this movement, which is actually much harder to do. I want to show, finally, one example that's taken from the Mississippi River. Back in 2011, there was that huge high water event in spring, and there was lots of threats to the levee. There was even a levee break in one area here, and you can see that these fields were entirely flooded. But what I noticed was actually in this area, field adjacent, where you actually see, in addition to, you know, this VV backscatter from the river and from the flooded area, you see an indication that you have more moisture in the soil. And this is the levee, and these are basically fingers of moisture coming in underneath the levee. So this indicates that there was seepage, and we classified the area and were able to identify the areas with the most seepage in an automated way. So we wrote an algorithm that could process this data in about 20 minutes. And the implication of that is that you could have this on board your aircraft and, you know, send this product, potentially in the future, this product could be sent to the ground from the aircraft in real time, near real time. And that's a pretty cool thing for emergency response. So that is all the examples I have to show you. I just want to say a few things, compare what I've been doing to, you know, where I'd like to be, you know, someday in the future. What I've been doing is a proof of concept. You know, you go out and you take a lot of measurements and you try to figure out what will make them better, what makes them work. It's kind of a prototype study. But to go from this to an operational program, you need to really, you know, make this slick. You need to, you know, it can't be Cathleen scientists doing this analysis. You have to automate it all. You have to integrate it with your decision support system. In advance, you need to know where INSAR is going to work. Do you have line of sight? Do you have trees, major, you know, big trees blocking you, so that you, in an emergency, you're not going to trust the data from that area. You have a mask showing you where you can trust the areas. You have to acquire a baseline so that you know the conditions before the emergency happens. And then you have to really develop and integrate all the products under test scenarios so that everyone believes the products and everyone's used to the products. And so that's kind of the difference between what I've been doing and where I think this program would have to go in order to be an operational program. And then during the event, you can get a single image with that pulsar technique that I showed from the Mississippi River example to look for seepage, and you can take your INSAR measurements from the same data set and try to show where there's movement, where there's major change. So this is the end of the talk. I hope that I've shown you some examples that show that this technology could be very useful for identifying change on earthen levees. And I think that the difference between what's been done before and what this has done is really doing it on earthen levees where you have low signals, low subsidence, small backscatter, and you need these long time scales in order to be confident of your results. And we are able to achieve the accuracy we did because we have acquired 51, flights over this area over a long time period. But in general, a simple assessment could tell you where INSAR is likely to work. It can tell you whether you have trees in the way, whether you have line of sight to that particular levee. And so you can actually, in advance, do a lot of work to make this useful during an emergency. So that's all. I hope you have a lot of questions. But I think we have to give you this.
Okay.
My question is the plan is to put the same instruments on a satellite, and then you would have the same resolution and the same ability to detect the. Would that be the same from being probably much higher or much further from the surface?
So the difference between the aircraft and the satellite is one, for the satellite, the image resolution wouldn't be quite as good. So you would have slightly larger pixels. But what we see isn't really one pixel. I'm sorry. So instead of being about 6 feet, it would be about 18 feet. About roughly a factor of 3 for your pixel resolution. And the other thing is the satellite would have a higher noise level. So you wouldn't have quite as good a measure in each measurement. However, it's compensated by the fact that the satellite goes over every 24 days or every 12 days, and so you get more images. You get a long time series, so all that noise is adjusted a little bit. Oh, I think he's next.
We're going to be looking at 360 miles of New Orleans levees this fall, and we're using technology that we developed for the Army. And I'm wondering if this kind of data can be made available to us for fusing. We've developed some methods for fusing with our technology, but we could work something out with use your data set. We've got about 1,000 miles here in the Delta. We've got a big project coming up.
Yeah, I think in principle, as long as you understand that we're still preliminary, we haven't done the final, calibration. So think of it as a relative measurement. And I'd like to get together with you after this and work with our collaborators at DWR, get you that data.
My question was, with the satellite going over every 24 days or something, it's only going, let's say, in one direction, and you have been doing it in 3 directions. What kind of difference for the interferometry would you anticipate less ability because of that? Right.
So one thing I talked about the fact that you're measuring movement in the line of sight direction. So if I'm looking at the surface like this, and it drops down, there's a change in the line of sight direction. If it slips sideways, depending upon exactly the direction that it slipped, I wouldn't be able to see it in some cases. So, but that's not, I'm looking for subsidence really, not for fault slip on an earthquake. It might be very relevant for, you might just happen to have a fault that's in the wrong direction for you to measure with a satellite. But it's less important that you only have one direction for subsidence measurements.
As this technology advances, I have an interest in using this for real-time flood fighting. And so, you know, under the state's SB 5 criteria and urban level of protection for a community, the state is asking that we have to acquire 10 feet of access at the landside toe or 20 feet of visibility, and that may include condemning properties for acquiring this access. They leave you an out that as technologies advance, can you supplant that need for access with drones and you know, this type of technology? So how far out do you think you are, or this technology is, from providing what flood control officials need for levee patrols? Is it 10 years out, 20 years out, 5 years out, for measuring seepage and slips and slumps and those types of things on a levee patrol?
Well, I think that technology-wise, we will validate this method in a year or two. But doing all the you know, things to make it an operational program, that's probably not what NASA's going to do. It's going to be someone else will come in and use this technology and make it that. I want to say, though, that flood, you know, looking at flood monitoring is much easier. It requires one time over, you know, you use the radar darkness. And so I think somebody could take radar imaging on even on a drone and do that now. It wouldn't require this extremely sophisticated instrument that can fly repeat tracks so well.
So you'd want to see that levee every 2 hours, let's say, or maybe an hour, depending on its past performance. You want to check, you know, sometimes there's technology out there, they claim you can see the temperature change in the soil because of seepage coming from the river versus the rainfall that came on the ground. And so, you know, there's a lot of trees on our levee system. Some people want them down, some people want them left in place. And so I'm trying to get ahead of the game and minimize impact to the community by using the available technology. But if it's not going to be ready for a period of time and verified and meet our standard of care, and we have to plan appropriately until it's ready.
Right.
My interest is in identifying areas around the Salton Sea that will contribute high dust emissivity during windstorm events. It seems to me that this technology could be used to look at elevation differences as small as a few millimeters to assess source areas for windblown dust. Do you see any limitations in the application of this sort of technology to that kind of problem?
Well, this technology does not work well on sand dunes, for example, because we're really looking for a shift in the surface. And on the sand dune, the sand is picked up and it's moved to a different location. And so the surface roughness has changed. All these things have changed about the surface. It's not like the slip of a surface or a slump of a surface. So you can look at interferometry over sand dunes and it just doesn't work. On the other hand, if you have a packed surface, you can tell, you know, changes on that level. Are you trying to identify where these high emissivity areas are? So maybe the salt content is different? It's possible that if it's a different type of soil, you could identify it with radar, not interferometry, with the polarimetry that I was talking about. Like it's used for identifying slicks on the surface of water, oil slicks, because the dielectric properties of the oil are very different from water. So salt's very different from unsalty soil, and you might be able to see something. You have to look at it.
I arrived a little late, so I'm not entirely sure if the resolution can do this, but could you do two images to produce a holographic image of the geometry of the levee, so that you could tell potentially where stresses are before you actually have a leak or subsidence?
I can't do that with this technology. At least I don't know. I think it's certainly beyond what's been done so far, so it's a ways out.
It wasn't clear to me how you're detecting seepage or moisture change in the soil. Is that what you said, that you can detect moisture change? Exactly how is that picked up? Are you measuring? I wasn't clear on that.
Okay. So we measure returns from all these different polarization orientations, and the relative change for the components from the different orientations gives you information about the soil moisture. Yes, it's a polarization change. There's a
resolution on moisture?
The difference as a function of soil moisture changes radically between highly saturated soil and very dry soil. So we're very sensitive at the dry end, but no sensitivity at the really close to saturated end.
So I recently saw a proposal from the U.S. Army Corps of Engineers to possibly put in reservoir islands on Bacon Island and Webb Track. Have you seen anything on either of those two islands, seepages or whatnot, that would make that a bad idea to put reservoirs there?
So what are the reservoirs, I'm sorry?
It's just a proposal that they have for potential, like, emergency reservoirs to store fresh drinking water on those islands, and potentially.
On Webb and Bacon?
Yeah, Webb and Bacon.
I don't know of anything that would stand out from those particular islands from the others.
Yeah, you said that you crisscrossed the delta from 3 different directions. As he said, if you have radar images from 3 different directions from the side, could a computer program put them all together and make a 3-dimensional image? I mean, that just seems easy.
You can make a 3-dimensional image of the deformation, of the change, but not of the surface itself. So you're not imaging the surface, you're looking at change. So yes, you can do that to get the 3-dimensional. But in the delta, it's pretty much like sometimes on the levees you might see some other effect.
So you mentioned that you had put together some algorithms. Are those algorithms available to use?
They're in the literature.
And so that was for the INSAR, but what about for the polarization change?
The polarization change I haven't published yet, but plan to.
And that to get that change, you did some sort of algorithm?
Yeah, but it's exactly what's in the literature for soil moisture change, for soil moisture detection. So you can find it in the literature. It's nothing special.
Can you venture a guess as to what it would take to get this implemented, how much it would cost and how long it would take? what the timeline might be?
Well, how long it takes depends on how many people you have on it, and how much money was put on it. So it's kind of a balance. I don't know. I don't want to say something on the web, and I really. Yes, it will. Yes. But yeah, I do want to say that this onboard processing has been demonstrated through, actually with this instrument. We used it in a Norwegian campaign this summer where we looked at oil slicks on the ocean, and actually were able to change our flight lines so we, imaged the right area. So a lot of work has been done towards making the technological advancements, but they're prototype stage, sort of, not yet operational, I should say. So. No, I'm sorry. I wish it were. Actually, this study is the most, it's the closest meshing of the state officials and the end users of any levee study that I know. I look at the levees in New Orleans, and I can't find a partner like I have here, or I haven't found the same level of partnership that I have here.
Okay, so it seems like this is all question we have. So thank you very much, Kathleen. That was very informative. For the next brown bug, we are likely to have one in August, mid-August, but we have not confirmed the date and content yet. But please be, I will send the emails as soon as we decided. So thank you very much all for coming here, and have a good day. Thank you very much.